It's my pleasure to welcome Archit Sharma today for our guest lecture. He's currently a research scientist at Google DeepMind, where he focuses on post-training and reasoning research. He's also a creator of the direct preference optimization DPO algorithm, which is really a foundational algorithm for aligning large language models with human preferences. And most recently, he led the development of the Gemini DeepThink model, the first AI model to achieve the gold medal on problems from the International Mathematical Olympiad. And yeah, with this, please give him a very warm welcome. And the stage is yours.
All right. Thank you for the introduction, Oier. And yeah, I'm very excited to talk to you all about scaling test and compute. All right. And my slides are visible, right?
Yes. Yeah.
Cool. Great. So I hope like everybody is like very familiar with LLMs these days. There's a few canonical ones that I've put up here. And these have really become an integral part of my life, and hopefully like a lot of us. Like these tools have billions of users. They're generating like an insane amount of revenue right now, and they're commanding such high valuations. And these really are giving us a peek into what AGI would look like. So a large part of the success of LLMs have resulted from the scaling of the computation that is going into it and put into the neural network machines that they are. And up until 2024, a lot of the improvements in these systems could be attributed to scaling the compute via pre-training. Pre-training is this large state it goes through where it scrapes a lot of the data from the internet and other sources, and it trains ever larger models. And all of these models are trained to predict the next token. So these become like really strong prediction machines, and it's a very scalable objective. And perhaps like maybe to a surprise of like a lot of the machine learning computing, scaling this fairly simple technique like allows the model to become a lot better in a very general way. So up until 2024, a lot of the gains in LLMs were a result of scaling the pre-training compute. Late in 2024 and early 2025, we started seeing the advent of these models, which perhaps are like attributed to like are basically the reasoning models. And the reasoning models, the key idea is that like these models are not instantaneously giving you an answer. They can spend some time thinking about what is going on, what the question entails, going through the context, maybe going through some tool calls, understanding the context a little bit more, and reasoning through that before giving an answer. And this really was a game changer for many different reasons. Up until now, the primary axis of compute which we were scaling up was during pre-training compute, but now we could like actually increase the amount of test time compute that these models use. And perhaps like very importantly so, when we increase the amount of test time compute that these models use, the model performance goes up predictably. So I've plotted a few benchmarks here from the Gemini 2.5 report. The first one is a benchmark called AMY 2025. This is an American math competition with a final answer problem. It's a high school level problem, which the LLMs were absolutely terrible at pre-2024. But as we can see that like the x-axis is the amount of time a model can spend thinking before an answer. And as this time increases, the absolute performance actually goes up by over 20 percentage points. And this is the same throughout all the benchmarks. Live Code Bench is a competitive coding programming benchmark, and GPQA Diamond is a science and knowledge benchmark. And all of these metrics go up as the model is allowed to think more and more about the problems. And up until like 2024, like a lot of the generational improvements were conditioned on pre-training. But if you look at this report again, Gemini 1.5 went to Gemini 2.5 Pro, and I've highlighted some of the boxes, and these are like dramatically large improvements in performance. And a lot of these benchmarks are coding or science and knowledge or math. And these benchmarks have gone up quite dramatically, and a lot of these improvements can be attributed to inference-time scaling here. Now, what is like inference-time scaling and test-time compute? A lot of the machine learning systems, or at least based on the neural networks, were based on like a fixed amount of forward computation. You get an input, you do a pass through some neural network, and then you do your prediction or your producer output. And this is a fixed amount of compute that a model will spend before giving you an output. For systems which have like test time built into them, they usually can actually spend a lot more compute before giving you an output. And the amount of compute they spend, there's some kind of a search procedure either in the output space directly or something of that form, which allows it to spend more compute than a single forward pass would have allowed the system to spend. And this ability to search and spend more compute on input is typically what is called like a test time compute system. The most prominent example of test time compute perhaps is AlphaZero. AlphaZero was a system built circa in the 2016 to 2018 kind of an era where these are the first neural networks to beat humans at an exceptionally hard game of Go. This was supposed to be a benchmark where like humans were supposed to excel and AI systems would never be at a human level. And one of the key examples in this, key things in this research was that when you have a model, which is a raw parametric model with a single fixed forward pass, it reaches about an ELO rating of 3000. So it is the leftmost bar in this figure. And when you have the same model and you add test time search on top of it, and note the search is capped to maximum of 5 seconds. When you add this search on top of it, the ELO jumps from 3000 to 5000. It's the same model just with test time search added on top. This was quite an insane result because 100 ELO points just for to note is like a 64% win rate, and a 2000 ELO cap is basically means that the 3000 ELO player could never beat, and the 5000 ELO player. And by the time you're around 3600, you're already absolutely superhuman. So the AlphaGo Lee was the model which beat the best Go player at the time. So this was one of the most prominent use cases of test time compute. But this is very, very much handcrafted to work for games and things which have access to a simulator. How do we enable LLMs to use test time compute? So there's this idea which came up in large language models, which is you can allow the model to have some kind of chain of thought-based reasoning before they answer. So let's say one of the cool things about large language models is you can typically prompt them so that they start following instructions much better. So for example, for standard prompting, let's say the model is told that it's shown how to solve a very, very trivial math problem. Roger has 5 tennis balls, he buys 2 more cans, blah, blah, blah. How many balls does he have now? The answer is 11. Now I'm asking a similar math problem, and the model is like going to give you an answer directly. And unfortunately, when you force the models to give an answer directly, they're typically not very effective at this. The idea in chain of thought prompting was that instead of forcing the model to answer correctly, the model is typically encouraged to reason through the math or reason through the steps before giving an answer. So Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls. 5 plus 6 equals to 11. The answer is 11. So it goes through these steps before answering the question. And now the next question, when it sees it, it is going to reason before it produces an answer. So the cafeteria had 23 apples. They used 20 to make lunch. So that 23 minus 20 equals to 3. 3 plus 6 equals to 9. So the answer is 9. And now the model is correct. So it kind of shows that when the language models start reasoning in natural language, they tend to produce more accurate and correct information as responses. This idea was exploited in this paper called Group Relative Policy Optimization from DeepSeek. And it led to a really interesting phenomena where if you warm start these models to reason a little bit and you do a lot of reinforcement learning with verifiable rewards, the reasoning sort of emerges over the course of RL. So if you can look at this plot on the right side, this is the RL training curve, and on the y-axis is the average length per response. And this model is trained on verifiable rewards, so situations where you typically know the right answer to the problem, or we can verify what the right answer is. So think about math problems, think about problems with code where you have unit tests. So when you train the models using RL on these verifiable domains, the response length naturally starts to grow, which tells that the model is now starting to reason in natural language. And on the left side, if you look at the blue curve, the model starts with an accuracy, the training accuracy of like 15%, and it grows to 80%. And this is all happening via RL, but the important thing is that the inference-time compute is also being used more and more through training and through evaluation as well. So, yeah, one of the coolest things that happened in this work was that it showed that reasoning emerges almost naturally over the course of RL, as long as you allow the model to use more inference compute. And this was a very fascinating phenomenon. It led to like a large set of improvements, both in open source community, but also this was being used in the frontier labs at the time. So the question then, like, I started to think about, and many other people also started to think about, is like, can we push test and compute more? So for LLMs, currently, like this kind of a natural reasoning regime allows you to do an inference time, scale the inference time compute via like chain of thought. And this isn't the only way to scale test time compute. So there are many other ways to scale test time compute. For example, you can allow the model to reason multiple times in parallel, and you can allow the model to take its previous answer and improve it over with multiple iterations. You can allow the model access to tools such as web search, code execution. You can allow it sandbox environments. You can allow like model to verify its own answer. And there's a lot of techniques you can use to increase the amount of test and compute the model uses and improve its answer. So this kind of scaling of test time compute led to many different kinds of reasoning systems. Gemini DeepThink, which I'll talk a little bit more about, is an example of such a system. But recently, if you've been using like any agentic coding tools as well, or if you have used deep research agents, these are all examples of what I think are scaling test and compute, but more through specific scaffold or harnesses around like an LLM system. So things like DeepThink or ChatGPT Pro are more general reasoning systems which can answer a variety of queries, but use an extended amount of inference time compute. But there's more specific harnesses as well. So Codex, Gemini Deep Research, Claude Code, Alethea is another example, like which are maybe more targeted research agents, but still use a large amount of test time compute. Now, Gemini DeepThink is a system I know a little bit more about, so I can talk a little bit about it. It's an amazing system where you can put an arbitrary amount of test time compute, and the model, in principle, should keep improving its response. Probably the most stark example of this was the performance of the model on this set of problems where it has to prove very hard math problems, like basically IMO level. And what we observed was quite surprising, is that if you look at the plot here, the x-axis is the amount of inference time being used on the log scale, and y-axis is the accuracy of the proof. So the proof is either correct or incorrect, as judged by an expert human. And I think the difference between the two curves is less important, but if we focus on the blue curve, it's pretty clear that as we increase the inference time compute, the model is like about 40% accurate to about 90% accurate. And this is, I want to clarify, this is quite a lot of compute. The model can work for hours here before it produces an answer, and it just keeps improving over time. So, and a lot of machine learning researchers love seeing like things which can be scaled and predictably improve performance. And this is one such example. Maybe perhaps like the interesting bit about DeepThink is that it's not just restricted to reasoning problems, not just math, not just verifiable things. The benefits actually do extend to like non-verifiable domains as well. So in this example, the model is asked to produce an HTML file where like it has like a whole voxel scene with cherry blossoms, trees, and like pagodas. And what I find fascinating is like 2.5 Flash, which is like a smaller model, to 2.5 Pro, which is a larger model, produces a fairly significant improvement in how the UI looks. But by scaling inference time compute that the model used, we see an even larger improvement on how many details are added. So if you look at the last picture, the cherry blossom trees have a lot more detail going on in them. The pagoda has so much more finer detail available to it. And all of this is like a function of increasing the test time compute here. So the point being that like a general extended inference compute system produces like improvements across many domains. And overall, like these systems are quite remarkable. As I said, Gemini DeepThink was the first system which achieved a gold medal standard at International Mathematical Olympiad, which was a goal or a milestone which was not expected to be reached in 2025. It's a very hard math problem competition. And yeah, on the right was like a tweet, but Codeforces is a competitive programming platform where like Gemini DeepThink, the latest version of it, like got an ELO of approximately 3445. And like to kind of ground this, there's only like 7 humans in the world who are like better at this than Gemini DeepThink. And if you follow along these days, like it's not just math competitions, new math problems that researchers are facing are being solved or at least being helped substantially by these models. And these scaffoldings like Claude Code now can like work for days to complete large engineering projects. So to kind of like put all of this in a nutshell, over the last year and a half, like test time scaling has been one of the significant drivers of improvements of AI systems, and like they're resulting in systems which are now producing real output in the world. Okay, so hopefully like I was able to like kind of tell you like all the amazing progress that has happened with test time scaling. So I'll briefly go over like kind of what is going on right now and what am I thinking about, or some of the like things like people at the frontier labs are thinking about. And yeah, with test time scaling, there's still quite a lot of open questions just related to fundamental optimization. I talked about how inference time scaling results in very predictable gains, predictable improvements across many domains. But the questions about like how do we do this efficiently, how do we use our tokens efficiently, how do we use our tools efficiently is still quite like an open question. And it's something we can make a lot of progress on. One of the interesting things about inference time scaling is that and maybe this is like maybe not slightly immediately obvious, but a lot of the success in pre-training was driven by increasing the depth of the model. And inference time scaling is actually, one way to look at it is like it is increasing the depth of computation as well. Because you're allowing the model to reason and produce more tokens before answering the question, it's doing more forward passes. So in some like loose sense, it is increasing the depth of computation too. The question then becomes like, what is the most effective way to increase the depth? Is it to increase the inference time compute through tokens, or is there other ways to increase depth of computation as well? And finally, like as showed results from agents which can do work for days or hours or weeks, we can like quite be sure that these agents are going to start working longer and longer and doing harder and harder tasks. So how can we make sure that these agents can do the work effectively? They're still making progress. How can we optimize the AI system so they're making progress even after a couple of weeks? How do we measure that they're making progress? How do we make sure that they're making progress safely? There's a lot we can do about this, and these are all open questions or things which are being worked on right now. And maybe to like, it might seem like a weird thought, like, do we really want agents to work for months? And I think like we can be sure that there's a lot of problems in this world which we would like these models to do. Something very simple and maybe, okay, I don't want to say simple, but like solving Riemannian hypothesis. It's very tangible that like there's $1 million prize that is associated with it. So like, and in practice, like the financial value of solving this might be even higher. So like at the very least, we can throw $1 million of compute at solving a problem like this. Now, same with like drug research, cancer treatment, or anything which extends human life or improves the quality of human life. There's a lot of value and a lot of compute we can throw behind such problems. And companies traditionally have made products by scaling the number of engineers. But now if you're building a new revolutionary product, like how much inference compute would you be willing to pay for to like build this like really cool product? I imagine a lot of. But I think it's also like useful for me to talk about that we have been scaling like inference compute. We are scaling how much work agents can do. And this is not going to solve every single problem that we face. And it will make a tremendous amount of progress. It will drive a large amount of innovation. But as an AI researcher, I think there's some still things missing, which I believe could be like interesting to work on. So one of the key things I think is knowledge discovery. Knowledge discovery, the models can solve well-defined problems extremely well by working like a lot of time, a lot of inference compute. But it's often hard for the models to figure out like what problems matter and what kind of impact they will have on the world. Recently, like Dennis proposed something called the Einstein test, which I think is an interesting thing where the model is asked to rediscover the general theory of relativity, training on data only up to like early 20th century, which is an interesting test about can the model discovering something like so abstract and something so revolutionary. So knowledge discovery is still pretty hard. And one other thing that I think is interesting and cool to work on is like, how can the agents improve with experience? Humans, when they work jobs or go through school or go through research, they typically become better researchers, better engineers, better at what they're doing. But agentic work, even though it uses a lot of inference compute and typically gets better, it can still be expensive. If you're doing a thing repeatedly, like you don't want to go through the same loop over and over again. And maybe another way to see this is like some tool calls or some things can be extremely expensive and reusing them over and over is not the best or the most efficient way to use compute. So we would like AI systems that can improve with experience, that form the right intuitions about the problems, that can shortcut rather than reasoning from first principle every single time they encounter the same problem. And this is something which would be like great to build AI systems for. And yeah, I think that's all I have to say for today. Hopefully like you see a little bit of peek into the frontier labs and like how we're thinking about test time scaling.
Hi, thank you for the nice talk. Most of this work on test time scaling is done in token space. What do you think the progress might be going forward in working on latent spaces for this test time scaling? Do you think this has some future? Thank you.
Yeah, that's a great question. So this is maybe perhaps like I was also hinting to is token space has a lot of benefits. A lot of the language models are trained to predict tokens and think in natural language. So scaling inference compute by scaling in the token space is actually very natural for the language models. This is why like reasoning emerges in things like GRPO. But it's arguably not the most efficient space to think in. The continuous space offers so much more space to represent thoughts, things which are maybe even more abstract. And you know, our language models, like the internal representations of them are in like continuous spaces. So we can consider scaling them up. It's much harder to get a system of that form working, but people are working on it, yes.
Yeah. Hi, thanks for the great talk. I wanted to ask, so one of the benefits of, or like side effects, I guess, of test time compute is a lot more data that gets generated from these conversations. And of course, as you kind of pointed out in your last point, of course, with experience, you expect these models to get better, hopefully. And so I'm wondering, like, have you seen any evidence of that already? And do you think future models would just create massive amount of shortcuts and not have to work for hours, but instead, you know, get trained on a lot of these external or like new data that got generated? Because I think 3 points that you mentioned related to like how to scale it is like parallel COT, right? Which I think you can definitely get shortcuts on or train like through training. Iterative self-refinement, I also think you can improve further. And so the last thing that remains is like web search. So I wonder if you've seen any evidence of that.
Yeah, that's a great question. So I think like there's early signs of like memories being used. People can create memories, or if you've like looked at skills, I think skill is a great example of like how like a lot of the agentic coding systems, like humans can add skills, or coding systems can remember things that they've done before, and that allows the models to like shortcut some of the things rather than rediscovering them. Overall, I think like there's some argument to be made that these are improving with experience, but it's still pretty manual overall. I think there's a lot of headroom or a lot of ways we can do that. But I think, yeah, this is very early on. I would say there's a lot of things we can do even right now.
Hey, thanks for the talk. For those of us that haven't spent time ourselves researching the methods in which we've had learned reasoning through verifiable problems, can you tell us a little bit about the challenges associated with moving from simple examples of verifiable problems, so simple math problems, simple coding problems, to scaling that to domains where today we're seeing models capable of working through very complex proofs, and what needed to happen to really scale it up to that point?
Yeah. There's a few set of problems. I think like first of all, like it's like maybe not well appreciated, but building the infrastructure is actually quite incredibly hard for RL scaling. The models need to train very, very stably. The models need to like not diverge in multiple different ways. The divergence can come through, so this is talked about in the open community as well. So like sampler training mismatch can often like exaggerate over the course of RL training, which can cause like a fairly bad divergence in performance. And there's a lot of like funny, quirky things that can come up, like the people spend a lot of time optimizing something like the compute efficiency, which allows the model to reach a certain amount of performance, so that in like a certain number of tokens over the course of training. The other thing which I think is important, and which is partly solved by the use of verifiable problems, but is that these things are extremely data limited. So verifiable problems are nice, but you run out of them fairly quickly. So you start off with easy problems, but as you train, and especially if these are like very strong pre-trained models, you run out of them very quickly, because very easy problems stop carrying any significant signal for learning for these models. So when you start reaching like the problem, like proofs or something of those form, math proofs are actually like not that easy to verify. So depending on how you do it, these things can still get hacked, and you have to work around these issues as well. So harder domains are harder to verify. There's fewer of them, so you have to be more efficient on learning of them. And then you have to also come up with like good methods that like allow you to scale inference compute in the ways we have talked here.
Hey, so you talked about scaling test time compute to maybe even months of work, but from our own experience, like models just make bad decisions at some point after days and they never look back. So is this because of like a jagged front line that models are good in one way but bad in other ways? Or how can we scale it up even more to months of work?
Yeah, that's a good question. So I think I think the models still make mistakes. The models will still get stuck in the wrong directions that, like I do so as well. Like sometimes I get stuck on the wrong idea and then I do not recover from it till like somebody pulls me out of it. So this is part of the problem we want to solve. So like when I talk about agents working for months, you don't want to like come back to it and it just hasn't solved or made progress. And the problem, if it is stuck, like asking somebody else or other agents or other humans to like help it better understand the problem. So yeah, there's still work to be done on this aspect. Part of it might be the jaggedness. These are really good at certain things. Part of it is like handling under specification. Often like the problems are not well specified and they misunderstand the problem and then get stuck. So there's a few things which need to improve for these models to be able to work effectively for on the order of months.
Cool. I think that's it from our side. Let's thank again Archit for a fantastic talk. Yeah.
It was great being here. Thank you for inviting me.
Yeah, thank you so much for taking the time. And see you soon, Archit.
All right. Bye.
Bye.